All right, so I said last time that we did a lesson that we would go back to doing a forces lesson. The last lesson was just more kind of theory questions. You didn't have any calculations. So we're going to do a few calculations in this lesson, but most of it is going to be applied theory. I'll throw a great little cartoon in the next slide, but I know lots of you are probably looking at me going, why do we need to know all this? We don't sit and analyze all of this as we work. But sometimes when we stop and think about why things work the way they do, learning how things work to the point of, okay, what are the fundamental principles, the most simple things that make up the basic mechanics of things, it helps us understand why it's so important for us to follow some of the rules, follow the recommendations. So I'm going to try to do some more of that, a little bit of think and apply in some really practical situations, and I'm sure you'll be able to think of some others. So it's not going to be all math. When we do get to the math section, I have posted a separate video of a guy that explains how to rearrange the force equation. So force equals mass times acceleration. So if you're not getting enough of that in this lesson, check out his lesson. He shows you how to do it with a triangle. And it's only about 2 minutes long, so it's really quick. So we're going to look at a second class of forces before we do a quick class on energy. So first of all, I want to kind of review. It's been a couple weeks since I recorded a lesson for you. It's possibly been a couple weeks since you looked at a lesson, unless you did everything March 1st when the last one was due. So first of all, I want you to think about what are the forces acting on a moving car? We have them all drawn here. So weight is the force that holds a car down to the ground. Weight is the force caused by gravity. So we talked about that a little bit in the last lesson. The reactive force upward is the force that the road places on the car. That force is critical, and we'll look at that in a few minutes. We won't actually calculate those two forces, but without weight being supported by a reactive force, your car would be in a sinkhole. It would fall through the road. So those two forces, they're always equal and opposite to each other. So the car pushes down, but the road pushes up. We can also relate that to our hoist. In the last lesson, one of the last things I discussed was, okay, if you have a car and a hoist, the car puts force on the hoist puts force on the car. That's the same thing as that reactive force. The two key forces that are involved in the motion of a car are thrust and drag. Now, there's a few really good videos that deal with this, and I'll admit your final assessment for this section, you're going to have a couple days to work at it. We'll give you a little extra time, but you're going to analyze, you're going to look at a few videos, and you're going to give me some explanations that aren't all math. Thinking about where some of these key concepts come from. Where's force used? Where's acceleration used? Thrust and drag, etc. There's some really nice videos, especially dealing with racing and that kind of thing, that I think are really helpful, and they can help you understand the principles a little bit better. So we're going to do a little bit of unconventional testing in this section, but I hope that's going to make it easier for you to understand. Now, thrust is the force applied by the engine, and drag is the force that opposes that motion. It's the friction forces that slow the vehicle down. Now, according to Newton's laws, let's kind of refresh what happens in some scenarios. So if the car is accelerating, so this car is speeding up, which force will be the largest? Well, let's think. If drag is the biggest, what's going to happen? Okay, we slow down. If you put more force from the engine, we speed up. So if thrust is the largest, we're going to have acceleration. If the car is decelerating, slowing down, that must mean there is less force from the engine and more force from drag to slow it down. So brakes are an example of drag. That might be a way for you to think of it. So when we press our brakes, we increase the drag by creating drag on the wheels, basically. So to slow down or decelerate, we make drag the largest. And what if the car isn't changing speed? Going down the highway, we're at a constant 70 kilometers an hour, we're not changing our speed. which force is going to be the biggest? Well, remember from last day, we said if there's no acceleration, the forces are balanced. So if we're not changing speed is what causes acceleration. So if we're not changing speed, that means we have balanced forces. So the forces are equal. Okay? So acceleration is always in the same direction as the biggest force. If the forces are balanced, we're not going to have any acceleration. Okay? So acceleration is in the size of the biggest force. So if my thrust is largest, the car moves forward accelerating. All right? If instead of if the thrust being largest, if the drag or the friction force is largest, that means the car is going to be slowing down. Eventually, it will come to a stop because the motion and the acceleration are in opposite directions. Anytime that the direction of acceleration is opposite, so if you think about forces, if the car is, the motion is this way, if the force, the biggest force, is in the opposite direction of motion, that always means you're going to slow down. It will eventually change the motion to a point where it could potentially change the direction. And that's maybe not so applicable for a vehicle, but that's what we often use when we're doing some of the technical physics equations. Okay? A little good refresh. According to Newton's laws, why do wheels turn? Another good example question, just a good refresh question. This takes us to Newton's third law. If you hear some rumbling in the background of this video, I apologize. I think I have my mic set up so it should cancel most of them out. My husband's having a good old drum jam. He always does this before I record. I'm not sure why. So when the wheel turns and it pushes on the road. Remember Newton's third law? It says for every action, there's an opposite reaction. That road pushes on the wheel, and that pushing against each other is what causes the wheels to turn. That's what keeps the vehicle in motion. So this is a Newton's third law. There's equal and opposite reaction forces. So the wheels push on the road and the road pushes on the wheel, which pushes the vehicle forward. Okay, if the road can't push on the wheel enough because of ice or water, those kinds of things, then our wheels slip. The wheel may turn, but it slips and it does not move the car forward. And that's because we have an unbalanced force happening there. So just a couple good little practical thinking questions. So for a quick refresh, we've already talked these, but just so you remember them, because we're going to need to use them for our calculations, we're going to do a few calculations. They're pretty easy. A balanced force means there's no acceleration. So the overall force is going to be 0 newtons. An unbalanced force means there's an acceleration. The acceleration depends on how heavy the vehicle is and what the force applied is. So the equation we're going to use is force equals mass times acceleration. Our force will be measured in newtons. Mass will always be in kilograms, and acceleration will be in meters per second squared. Okay, so we're going to just do a few easy calculations calculating some force. First one, what would the overall force be on a Nissan Micra if it accelerates at 2.4, it should be meters per second squared. I'm going to actually just write that in here because I'm mistyping it, and has a mass of 1,200 kilograms. So we need to use the equation for force. The equation for force is equal to mass times acceleration. Now, if rearranging this gets tricky for you, please take a minute and check the other video out, but I think you'll find the rearranging is really easy. So force equals mass times acceleration. We want to know how much force we need in order to accelerate it. So what's the force? This would be the force if you take the thrust from the engine and the drag of the car and you subtract the two, how much force would there be? Now 1,200 kgs is roughly the actual weight of a micra. 1,200 kilograms times 2.4 meters per second squared. Kilograms times meters per second squared will give us newtons. Putting that in our calculator, we get 2,880 newtons of force. That's what you would need. Right? Pretty easy calculation. No real rearranging in this one. Okay, let's go to the other end of the spectrum. We've got a Ram truck, and it accelerates at the same 2.4 meters per second squared, but it has a mass of 7,300 kilograms. How much force do we need to get that truck to accelerate? I think this probably explains, I mean, we all know that the bigger the vehicle, the bigger the engine we require, but this calculation proves it. So our force, I'll write the variables out. It's mass times acceleration. The little dot just means multiply. If you want to draw the multiplying sign, you can. So 9,300 kgs times 2.4 meters per second squared equals, now that we have those two, I wrote it down, but I flipped the page over. 17,520 newtons. It's a lot. It's a lot more force. So by comparison, the micra needs 2,880 newtons. What's the difference that makes the big change in force that you need between the two? It's the amount of mass. The truck has so much more mass, it doesn't want to change its motion as easily, so it requires more force to do so. Therefore, it requires the larger engine. Yes, the larger engine adds weight, but it's required in order to move the overall mass of the vehicle. It also means if there's a collision between the two vehicles, the two of them hit each other. When they hit each other, remember the force is at impact. When the two hit each other, the force on the micra and the force on the truck would be the same. We're going to find that the micra, because it's so light, is going to have a huge acceleration where the truck's not going to have a whole lot, which is why the truck usually keeps moving and the little car stops and bounces. So it is true, big vehicles tend to be safer. They also tend to use more fuel, because we're going to find that energy is related to force. If you need more force, you need more energy. Pretty logical. Physics is really pretty logical. Lots of times people panic about physics, but if we stop and think about it, it's really logical. If both vehicles come to a stop from the same speed in the same amount of time, what would this tell you about the force that the brakes can apply to the wheels? So we've got our two vehicles. We just found that in order to get them to speed up at the same amount, the truck uses a huge amount more force. So what about if we have to stop them in the same amount of time? What can we predict about the brakes from that? Well, the truck is large. It has a big mass. So it needs more force to stop. Say more braking force. Okay. The car, on the other hand, is light. It needs less braking force. So what can we predict about the brakes? Well, we're going to have bigger brakes, or brake that can apply more force on the truck than we will on the car. It's just one of those. The other thing that, and I found this from working, now different vehicles have different tendencies. We used to have a Honda CR-V, and the Honda CR-V went through brakes very quickly compared to our Sentra. And I was told that that's just one of the things about that particular vehicle is it tended to wear through brakes more quickly. And well, I have an example at the end of a brake problem that we often had with that vehicle. that we can talk about forces to kind of explain how we always knew when it was happening. But one thing I notice is we have a Pathfinder now. Pathfinder is substantially larger vehicle compared to, we had a car as well. We had a Sentra at one point. And the difference between them, the Sentra didn't need brake repairs nearly as often, whereas the brakes on the Pathfinder, they're more expensive, but that's because they're bigger. They need more force to stop. There's a lot of force in that vehicle. It's one of those things to remember when you're doing brakes on a vehicle is those brakes have to be able to apply a lot of force. So make sure when you install them, everything is seated properly. That's really important because you have the life of those passengers in your hand when you're doing that repair. We often don't value that enough. That's one of the unfortunate things. Sometimes we don't put enough value in tradespeople. We kind of forget that their lives are in our hands in those cases. But we always find it's more expensive to replace the brakes in the Pathfinder because they're bigger. The other thing is a heavier vehicle, so it goes through brakes a little bit more. Thankfully, I don't drive it very much. It's just driven mostly around town. But that was one of the things that we noticed. So a larger vehicle, as for those of you that can't wait to get the big truck, and those of you that already have the big truck can probably confirm it, the larger the vehicle, the more force that vehicle requires, A, to drive, B, to stop. That means you're going to have more wear and tear on parts on the vehicle because there's more force. Now, parts are designed to handle the bigger truck. You definitely wouldn't take parts for a Micra and put them on a Ram. Even if you did lower it to a ridiculous thing where it looks like a car. I still don't understand why people do that. But then again, I'm not really a car person, or a truck person, put it that way. All right, so hopefully that gives you a couple practical examples to think about. And this is not something that we're doing calculations with, but our calculations prove what we probably already knew. So you will need to use this formula, but more importantly, can you think and apply about what's required for force and why is it important to check, double check, and triple check? All right, another couple questions. Similar, they're going to use the same equations. So an engine in a 2,500 kilogram car applies 8,200 newtons, while drag causes 7,500 newtons of force, opposing force. I think I missed a word in there somewhere. How much force is moving the car forward? Well, let's see. The engine can put 8,200 newtons. Drag slows it down with 7,500 newtons. How much force is actually moving it forward? Well, you'll notice forces are in opposite directions, so some of it's going to cancel each other out. So let's figure out, well, how much force is actually still going forward? So 8,200 minus the drag, because drag doesn't give us any forward thrust. It subtracts from it, leaves us with, I think it's 700. Yeah. I honestly wasn't even really looking at the numbers I was written down here. So we have 700 newtons still actually moving the car forward. The rest of the force is just counteracting the drag, or the vehicle wouldn't move at all. What's the acceleration of the car? Well, acceleration is easy to find. We use our formula. Force equals mass times acceleration. Now, we have to be careful. You can only use the force that's moving the car forward. So not all of the thrust is moving the car forward. Some of that thrust is counteracting drag, but all of this 700 newtons is moving the car forward. So we're going to use the 700 equals the mass of the vehicle is 2,500 times our acceleration. Divide both by 2,500. And acceleration is equal to 0.28 meters per second squared. And that's our other number. So really not too difficult to calculate. You think about what forces are opposing each other. Now, I'm not going to give you the answer to this, but there is going to be a video that's going to come up for you to analyze or to think about. In racing, sometimes you can't put a bigger engine in to get more thrust because you're maxed out at whatever weight that vehicle is classed for. So what they do is what they call, there's a couple things that they do, but they've got in the words totally, they drafting, get really, 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 really close behind a vehicle. And technically there's a little vacuum that is created behind the vehicle and it pulls the vehicle behind it forward. It actually will, instead of causing drag, it adds to that thrust so it gives a little bit more force. I'm going to give you a video to watch on that, and you're actually going to do a little bit of what happens if and thinking about some forces on it. But it's actually a really cool video about how drafting behind a vehicle or bumping is another thing that's used, can be used to actually get more speed on a track. Definitely don't recommend it on the road. Another thing, my grandfather, he was very Scrooge, and maybe from an era where some things were allowed that aren't necessarily now. But when he was going on a trip, according to my mother, I was never with him when this happened. This is when she was a girl. He used to always get behind a transport truck. The reason he would get behind a transport truck is it made his fuel efficiency better. Also probably a relatively dangerous practice to get too close behind, because if they have to change speed quickly, you don't always have as much time to know what's going on, to notice what's going on and respond. But the reason he would do that is because A, it made drag smaller. So if we can make drag smaller, we're going to have more, the engine doesn't have to work as hard to compensate for it. And it would actually add a little bit of forward motion, a little bit of forward, add like some vacuum, some pull, some force to pull the vehicle forward a little bit so the engine didn't have to work so hard. If the engine doesn't have to work as hard, don't use much energy. So that was my grandfather's strategy. But he had a few weird strategies, like you should always drive a red vehicle because fire trucks are red and red vehicles are safer. I have no idea if there's any truth to that, but there's some random things from a man that would now be well over 100. So he might have had a few strange notions. He came from horse and buggy days at the beginning. But while he never had a physics course, he definitely understood how thrust and drag worked in order to get the best fuel efficiency. All right. This example, we're going to modify our picture a little bit. The engine of a car is turned off, allowing it to coast, and the brakes, I think I wrote brakes instead of brakes. Anyway, the brakes are applied. The car has a mass of 1,780 kilograms. It decelerates from 85 meters per second to a stop in 3 seconds. What's the deceleration of the car? And how much force do the brakes apply? I'll have to change the spelling on that one. Well, first of all, let's look at our picture. We don't have to worry about these two forces because they're just keeping the car on the road. So we can kind of ignore them. But if we turn the car off, is there any thrust? No, there's no thrust from the engine. So there's no forward. The car was moving. This is the motion of the car. And the only force is a drag force from brakes. So this is the force of our brakes. Pulling it backwards, causing it to slow down. Okay? So we need to figure out, well, how big is that force? What is it that's slowing it down? Well, first of all, we need to figure out the formula for force is mass times acceleration. I know how much mass the car has, but how much is the acceleration? We want to figure that out. So that's what we'll do first. Remember, acceleration is the change in velocity or the change in speed divided by how long it takes to do the change. So it goes from 85 to a stop, 8.5 to a stop, which means it changes 8.5 meters per second. Divided by 3 seconds gives us an acceleration of 2.8 meters per second squared. Now we can figure out how much force. Well, it's 1780 kgs. This is fairly small vehicle, times 2.8 meters per second squared. The brakes need to be able to apply 5,043 newtons of force. Now, technically, you could argue with me on that. You could say, well, that doesn't all have to come from the brakes because you just told us that the vehicle has some drag on its own. And it's true. It's true. But you don't have the ability. And we'd have to do a 2-year physics course in order to deal with all of this stuff associated with drag and calculating drag. So we'll just treat this as all coming from the brakes. The brakes don't have to apply quite that much force, but it definitely has to be able to make up for the amount of drag. Or the amount, yeah, it has to be able to make up for whatever drag can't to stop it more quickly. Hopefully I didn't muddle those words up. I feel like I kind of got tongue-tied. All right, one more question with math and then just a couple thinking questions. Gravity pulls down on objects with an acceleration of 9.81 meters per second squared. How much force does a 7,280 kilogram truck put on a hoist when it sits motionless in the air? So I'm not going to draw a truck, I'm just going to draw a box. Okay, so here's my truck. And it's sitting on my hoist. And we're going to ignore the hydraulics part. We'll get to that later, but not in this section. This section, we want to break things up so they're small and manageable. Okay, so the truck has a force down. The hoist has a force that's up. Okay? So the hoist pushes up, the truck pushes down. How much force does the truck put on the hoist? Well, the force from the truck is going to be equal to the weight of the truck times the acceleration. Well, you say the truck's not moving. No, it's not moving, but gravity always pulls down with an acceleration force, with an acceleration of 9.81. So the force that the truck puts on the hoist is always equal to mass times gravity. Now, lots of times we'll just think about it in terms of just how many kilograms, because we don't usually do repairs in Mars, even though you might have customers that you think would be better off landing there. You never say that to them. That wouldn't be good customer service, just in case you wondered. But the force applied in newtons is 71,400 and we'll say 17. I'm going to round up newtons. It's a lot of force that's put down on that hoist. Also, one of the reasons why you have to make sure you're rated for the right amount of weight. So the force is 71,417 newtons. How much force does the hoist put on the truck? Remember, it's not moving. If it's not moving, what does that tell you about the forces? They have to be balanced. So if it's not moving, it's motionless. If the truck pushes down with 71,417 newtons, the hoist pushes up with 71,417 newtons. All right. Last piece. Using Newton's laws, why is it important to jack or lift any vehicle using solid frame components? There's a lot of force. A-L-O-T of, there's a lot of force and you have equal and opposite forces. You have equal and opposite forces. So the same force that the vehicle pushes down with is the force that the hoist pushes up with. And if for some reason, where you have the vehicle, I'll say braced for lack of a better word, the point of lift, if it can't withstand the amount of force that the vehicle pushes down with, well, you're going to have something break or bend, or your life could be in danger if you're working under it and your jack can't support the weight, can't support the force. So it's important to use solid frame components. Also extremely important to make sure that you're not jimmying jacks to get a job done without having the proper tools for your own safety. You never want to hear of somebody getting hurt or injured. Also a reason why it's really important to make sure things get inspected on a regular basis to make sure that wear and tear doesn't mean they can apply less force, because the same force that the car pushes down with is the same force that jack has to be able to apply upward. So just logic statements that we have shown physics can support. That's the whole reason of having a physics section in your course. The last two questions are questions that are taken from examples that I know are real life. I know they've happened before. Maybe not exactly as they're worded, but very close. A friend has a vehicle with a frame and body in rough shape. The wear has compromised the strength of the frame to the point that it won't pass an MVI. They tell you the car still runs perfect, they aren't doing any long distances, and they want you to fudge an inspection. Without thinking about would you do it or would you not do it, I want you to ignore the fact that an illegal inspection could cause you to lose your license. I know they exist out there. It's risky. How could you use Newton's laws to justify that putting a sticker on the car, providing a sticker, puts the driver at risk? So we're going to ignore everybody else. We're just going to think, because lots of times people think in this kind of scenario, well, I don't drive very much. I'm not really putting anybody else at risk. I know my car won't stand up in a collision quite as well. Okay. So we're going to ignore the fact that whether the brakes are good, they were able to stop, all that kind of stuff. It's just the frame's rusted out. We had a car that was like that. Frame had rusted out. We sold the car as is. Interestingly, somehow the car couldn't be inspected. Somehow that car got a sticker and drove around for a few years. And I know it was the car because, drove the car. But that's one of those things where, what do you do? You say, well, just this time I could pass it. Well, is that safe? Why, from a safety perspective, do Newton's laws say that we shouldn't do that? Well, the biggest thing is the person in the vehicle is going to be at more risk. That frame is meant not only to hold all the components of the vehicle, but that frame is designed to prevent injury during impact. It's designed so that if there is an impact, your car doesn't crumple to nothing. That's one of the biggest reasons why there's recalls on them. It's not just that the car is not going to look good on the outside, because lots of times you don't know what's under a car. People don't look necessarily, especially if they're not car people. So you might not see what's underneath, but in a collision, what's underneath is exposed. If that frame can't support the impact of a collision like it used to, it may mean the friend that wants you to fudge a sticker loses their life in a collision. It might not impact the person they hit, other than the trauma of having somebody die in a collision that you were in, and that is traumatic. But that's one of the ways we can use Newton's laws to justify it, is that if your frame can't withstand the force that would be required when you decelerate, it could put you at risk in the case of an accident. So just some of those really practical examples to think about, and sometimes maybe it helps us, gives us reasons to follow the rules rather than to break the rules, as much as I hate doing unnecessary work to vehicles. But there are certain things that I keep a very close eye on. Brakes is one of them. Anytime I think brakes are potentially compromised because of Newton's laws, and I understand how those work, I know that those brakes need to be strong in order to keep me safe and you safe on the road as well. But this is a really good question about how frame strength is really important to vehicle safety. And it all hinges on Newton's laws and force. This is another issue that, remember I said that CRV that went through brakes often? We loved that car. We had it for about 10 years. It was one of our favorite vehicles. And if they still made the old school style from 2006, I don't like buying new vehicles, but my husband and I would probably agree to buy a new one. It was kind of like a truck, but drove like a car. It's great. way better than the Pathfinder, which is a four-wheel drive minivan, if I'm honest. I don't know what you think of them. Hockey moms love them, but I'm not exactly a hockey mom, but it does its job. I just can't haul stuff in it like we used to do with the old one. I actually have to use a trailer. So in this situation, though, this is something that happened often with our CRV every year. And it's one of the things, I was usually the first one, even though I didn't drive it the most, I was usually the first one to notice. And I'm going to give you a couple of things that I saw. So if a caliper is sticking slightly on a brake, that should be a comma there, fuel efficiency will drop. And sometimes the vehicle has a dragginess, even before you get the telltale hot smell. So oftentimes if a caliper is sticking, you'll feel a wheel hot. But there's sometimes when maybe it's not sticking enough to feel it hot, or the air temperature is cool enough to keep it cooled down to the point where you don't notice as much. Maybe just your sense of smell is off. But one of the things I observed every time we had a sticky caliper was fuel efficiency would drop. So we'd suddenly notice we weren't getting quite as many kilometers out of a tank, and it would just feel draggy. When I was stopped and I went to start, you always felt like you had to give a little more gas. And even once you got going, you always felt like you were giving a little bit more gas. It just didn't want to drive the way that it should. Okay. So according to Newton's laws, why do I feel like I need to give it more gas to get the same speed? Well, let's just think. I'm going to think about a diagram. This is my car. If I have a sticking caliper, so let's say this is my normal drag. Normal drag, that's what I'm used to feeling. If I have a sticking caliper, I'm going to feel a little bit of extra pull, a little bit of extra drag. So I have more drag. So what do I feel like I have to do with the engine in order to balance that? I need more engine push. It has to be larger. The engine push has to be larger than the drag and the stuck caliper in order to get that vehicle to start moving, to get off a zero line. So that's why I feel like I need to give more gas. It's because there's too much force in the other direction. I have to add more force so that I can accelerate. More force than usual because we've got extra drag. So that was one of the first things I would notice. And I still watch fuel efficiency for brakes. It's one of the easiest things to kind of keep an eye on. If fuel efficiency changes dramatically in the vehicle, I usually start, I don't frig with diagnosis. Brakes are one of those things that for some reason I seem to be able to usually pick out. But I'll usually go heckle my husband and say, hey, wait a second, something's going on here. I think we need to check this. And I'm just in my best hunch, and he actually figures out what's going on usually. Okay, now let's address the other scenario. So that addresses why I need to add more fuel. The other thing that sometimes happens is sometimes you feel like you have a pull to one side if you've got a stuck caliper. Why would Newton's laws justify that? How would that be? Well, let's draw our vehicle again. We'll use it as a box. And I'm going to pretend, well, we have two-wheel drive or four-wheel drive. I had a four-wheel drive vehicle, so we'll put force on all the wheels. So we've got force applied from the engine. So some thrust there. We've got force applied on this wheel. And I've got force applied on this wheel. And I've got a stuck caliper over here. And I've got force from the brake going the other way. Okay? Are the forces all balanced on that car? No, the forces aren't balanced. If the forces aren't balanced, this car, well, it's going to want to probably pull that way. This wheel is dragging. These wheels are pushing faster, so it's actually going to cause the car to turn. We call that non-concurrent forces in physics. We don't deal with that with you, but the whole principle of The forces aren't balanced, so it's going to accelerate. And the acceleration can be a change in direction. So that's one of the things that happens. And that's why you feel that pull, is it's the whole unbalanced forces due to Newton's laws. So hopefully that gives you some practical examples of where Newton's laws are involved and how they work and why they work the way they do, and some places where maybe you don't calculate them at work, but places where you will see them in action in your trade. All right, so that finishes off that section.